To a video here on parametric equations and calculus. So last video we learned about parametric equations in general, just kind of re-familiarizing ourselves with them. But now we're going to actually be taking the next step into calculus for them. So here are a couple of formulas here. So if you have a smooth curve, again, smooth curve really just means it's differentiable. It's all you need to worry about. Given by two different equations, an x equals and a y equals equation, both in terms of t. So don't get too tripped up on those f of t, g of t. And the slope at that point, x comma y, can be given by right here. So dy dx is the same thing as dy dt over dx dt, where dx dt cannot be 0. Because if dx dt is 0, then that's going to be a vertical tangent. The second derivative is given by, take the derivative of the original one, which turns out to be the derivative of dy dx all over dx dt. So these are just things you need to memorize. A lot of people just think that you just add the dt in the bottoms here, which I guess is technically true for the first one, but it's not the same case over here for the second derivative. So I just want you to memorize these. Take the derivative of the top, take the derivative of the bottom, divide them. Sorry, when I say top and bottom, I mean y and x. And then second derivative, take the derivative of whatever you get here, and then divide that by whatever dx dt is. Okay. So let's go ahead and just practice these very basic formulas here. We have two parametric equations. We have the x equals t squared plus 9, and we have y equals, these are both fairly simplistic t functions and for x and y. Y equals 4t to the fifth minus 6t cubed plus 3. Okay, so real quick, let's go ahead and find out what dy dx is. So dy dx, it's going to be dy dt on top. So it's the derivative of the top one. Sorry, top one. The derivative of the y1. So the derivative of the y1 here is just going to be 20 t to the fourth minus 18 t squared all over our derivative of our blue, which is going to be just 2t. Okay, and then we can simplify that a little bit here. I just color-coded this for you so you can see which one's which. Top has a GCF of what here? Well, actually, you know what? I don't really care about the GCF so much. I know that I can divide both of these by 2t's because I want to leave it in expanded form because I got to take the derivative again here. So I don't really want to factor it so much. But I can divide each of these by 2t. So 2 goes into 20 10 times. T goes into t to the fourth. To make that a t to the third minus 18 over 2 is 9. That's going to become t. So there you go. There's my dy dx. Now for the second derivative, that's going to be the derivative of the top here. So the derivative of the top here is going to be 30t squared minus 9 all over just my dx dt, which I already found, which is just 2t. Okay. And then this is perfectly fine right here. I'll just simplify this. How long has this been here? Hopefully not too long. Sorry, did not know that my screen had some random pop-ups on it. I do apologize for that. Recap, because I don't know how long that thing was on the screen for. Derivative here, just take the derivative of the y over the derivative of the x and just simplified it right here. That's all I did. And then for the second derivative, took the derivative of the first derivative, which is the brown one right here, all over derivative of x, which I previously had. Just to simplify this real quick, this is going to turn into 30 over 2 is 15. T squared over t is just t. Yeah, just whatever. Minus, and this is just going to be 9 over 2t. That's really about it. Just two different ways to look at it. These both are acceptable. Okay. Typically, when these are asked, they're not really just asked like straightforward, like, hey, what's the second derivative? They're usually asked in some type of context. So don't worry about the simplification too much. Okay, so this one is more of a context one. So we're given the parametric equations of x equals 5 sine t, y equals 3 cosine t. By the way, that is an ellipse. Write the equation of the tangent line to the curve at the point t equals 2 pi over 3. So all we're going to do here is just find our find our derivative, and that'll give us our slope. And I want the tangent line, so I need to find out what the x value is, what the y value is. I'll do that first because it's really not the calculus part of it. So I need to find out what x of 2 pi over 3 is, and that's when I plug this in. 5 of sine of 2 pi over 3. So 2 pi over 3, that is in the second quadrant. So it's going to be positive here for sine. So it's going to end up being, I just want to double check myself here, make sure I'm everything there. Yep. Okay. It's going to be a root 3 over 2. Second quadrant is positive. Root 3 over 2, so it's going to be 5 root 3 over 2. And for the y, is going to be 3 cosine of 2 pi over 3. And then cosine 2 pi over 3, it's going to be negative second quadrant. So it's going to turn into a negative 3 halves, I believe. Negative 3 halves, yes. Negative 3 halves. Okay. Yeah, look, you know circle stuff, you kind of have to know. So there's that. Let's go ahead and find slope. To find slope, I'm going to have to find the derivative. And then I'll plug in my 2 pi over 3. So my derivative of my top here is going to be, for y, negative 3 sine of t all over derivative of x is 5 cosine of t, which I can make that look a bit nicer. I was like, I think I want to make that look a bit nicer. This is going to be negative 3/5. That makes a tangent t. You don't have to do this, but I think it's just easier because I was just like, I don't want to put it in twice. So now to find the slope, dy dx of 2 pi over 3, I'm going to get negative 3/5 times tangent of 2 pi over 3. Second quadrant here, so tangent's going to end up being negative. This should be root 3. Yes, root 3. So this should end up being a, it should be negative. So negative is going to cancel out. You're going to end up getting 3 root 3 over 5. Just plug all this stuff in now. Because usually we have y minus y1 equals slope x minus x1. Well, I have this now. So y minus y1 is, that should be a, let's try it again. Y minus y1 is negative 3 halves. Slope is 3 root 3 over 5. And this is going to be x minus this 5 root 3 all over 2. So there you go. There is the equation of the tangent line. All right. So a little bit of application here. With some more applications here. Okay, so find all the points of the horizontal and vertical tangency of the parametric equations here. So just go ahead and find dy dx. It's all we need to do. And then what's going to end up happening is, okay, well, I'm going to use this one right here. So horizontal is when we set dy dx equal to 0. This is horizontal. And I'm keeping this here for a reason. So if this is equal to 0, that is when dy dt equals 0. Okay? For vertical, that's when dy dx is undefined. Look at my equation here. Well, it's undefined when dx dt equals 0. Okay? So if I find dy dt set equal to 0, that's your horizontal point of tangency, and then set dx dt equal to 0, that's your vertical point of tangency. Okay, so let's do it. So for horizontal, I'm going to do dy dt is equal to, so like just do 2t minus 8, which I do want to set equal to 0, so I'm going to end up being t to equal 4. So it's horizontal when t is equal to 4. So when t is equal to 4, well, x of 4 is, I'm just going to have to look at my notes because I don't really feel like doing all the math. It's going to be 24. and I plug in a 4 for y, I'm going to end up getting -7. So you found your t value, plug it in. So my horizontal point of tangency is 24, -7. For my vertical, I'm going to do dx over dt equal to 0. So dx over dt is going to turn into 6t minus 6. Set that equal to 0. So this is going to be t to equal 1. So when I plug in a 1 here for x, again, I don't really feel like doing the math, it's going to be -3. Plug in the 1 for the y, and that's going to give me 2. Right? Yep, 2. That makes sense. 2. So this is going to be the point, -3, comma 2. So there's my answer for my vertical. Here's my answer for my horizontal. So just be careful with these parametric equation stuff, because since you have that extra variable of t, you're going to need to use it. All right, so set up the integral expression for the arc length of the curve given by the parametric equations. Do not evaluate. So you have these totally way out there parametric equations. Arc length, well, let's kind of look at arc length down here, because this is another little formula that we're going to have to memorize. Okay, so arc length for a parametric graph is right here. So S is going to be integral from A to B. This one gives us A to B. Super nice. Usually do a phrase. And then it's going to be the derivative of x squared plus y squared, all with respect to t, by the way, dt, square root over that. And if you want to know why that is true, here is the entire computation of it, which is really, really neat and nifty. I like it. I'm a fan of it. So if you ever want to see why, there it is. But let's just go ahead and do the problem here. So essentially, we just need to find out what dx dt is, what dy dt is, and just plug it in. It just wants the setup. Let's do it. So dx dt. This is going to be just a little bit itty bitty of chain rule here. Derivative of the inside is going to be 5. Derivative of the outside, just e to the 5t plus 2. dy dt is going to be another little itty bitty chain rule here. So we're going to get 2t out in front. So it's 2t times 3, which is 6t. 6t, and then cosine inside stays the same. All right. And then all we do is just plug it in this formula. So the arc length is going to go from A to B, so from 0 to 4, of square root of 5e to the 5t plus 2, and that's all squared, plus, this is going to be 6t cosine of t squared, and that is all being squared, dt. And there is a setup. It is common for AP to ask you setups only on these as well. This would have to be a calculator question anyhow, because we do not know how to find the integral of that bad boy. All right, and that's going to wrap it up for parametric equations with calculus.